Hi, I'm Sara from IMT North Europe, and I'm here to present my work on adaptive Gaussian nested filters. These filters belong to the nested methodology framework, and they aim at estimating both the parameters and the state of dynamical systems. This is a joint work with Victor Elvira from the University of Edinburgh. So, as I said, we are interested in dynamical systems that can be represented with state space models. These models have two random variables that describe them, the state xt and the observations yt. Both are usually noisy and can be described by a couple of functions that depend on the parameter theta. This vector is usually unknown, so if we want to estimate the time evolution of this system, we need to estimate both the parameters and the state. There are a lot of approaches that try to solve this problem, but in the last years, there have been some new methods that aim at estimating the joint posterior distribution of both the unknown variables, the state, and the parameters theta. Those methods belong to the nested methodology framework, and they can quantify the uncertainty, so we can measure how certain we are about our estimates. They can be applied also to a broad class of models. And finally, they provide theoretical guarantees. So the convergence is assured. The structure of this methodology is a divide and conquer approach. It has two intertwined layers of computation. The first one is used to estimate the posterior distribution of the parameters given the observations, and the bottom layer is used to estimate the posterior distribution of the state given both the observations and theta. And with these two posterior distributions, we can reconstruct the joint of the parameters and the state. So within this structure, in the top layer, we implement a sampling filtering technique. So this predictive PDF is going to be represented with a set of n samples of theta with the respective weights. Once we have that, we can run or implement in the bottom layer n different filters, one per each sample of theta. So we can run a standard filtering technique that estimates both the predictive distribution of the state and the posterior one. The key here is that in this bottom layer, we can compute the evaluation of the likelihood of each sample of theta that we are going to need in the top layer to the update of the distribution. There have been many different implementations within this structure, but our goal within this paper is to reduce the computational complexity of this structure without compromising the performance. And for that purpose, we are going to play with the number of samples that we are using in the top layer of the filter. So we have proposed the adaptive Gaussian nested filter, that is the first nested method that adapts the number of samples of the top layer of this structure. The adaptation is achieved using two novel mechanisms. The first one is an adaptive rule that reduces automatically the number of points when t grows or when the parameters are close to convergence. And the second one is a recursive rule that determines when the filters of the bottom layer can run recursively. So we do not need to reprocess the whole sequence of observations. For the adaptive rule, we use a statistic rho that is built with the evaluations of the likelihood of each theta sample. So this statistic takes its minimum value, when only one of these evaluations is different from zero. So only one of the samples is able to give good approximations or good estimates of the state. The statistic takes its maximum value when all the evaluations are equal. This happens usually when the parameters are very close to convergence and the posterior distribution that we are approximating gets very narrow. So all the points are very close in the parameter space, and they basically provide the same evaluation and almost the same estimations. So we might consider that the points might be redundant. So in the adaptive rule, we check when this is the case. When rho is very close to its maximum value, we decide to reduce the number of samples. Otherwise, we keep the number of samples as it was. As the filter was explained until now, it's not recursive. Every time we make an update in the top layer, the samples of theta are recalculated, so the bottom layer filters, the ones that estimate the state, should have to start from scratch. If we want to make this filter recursive, we need to assume that the posterior distribution of the state given the new sample is going to be approximately the same that the posterior distribution given the previous sample of theta. And when is this a reasonable approximation? When can we take this approximation without introducing much error? So we are going to compute the norm between both samples, the new one and the previous one. And we are going to compare this norm against a prescribed threshold lambda. If we are below this threshold, we are going to take the approximation. If we are not, then we assume that this approximation would introduce too much error in our estimate, so we start our bottom layer filter from scratch, starting with the prior of the state. For more details, you can check our paper, you can send me any questions by email, and of course, we can meet at the ICASSP 2023, where I'm presenting my poster with this work. So thank you for listening and see you there.